In today's episode, we're going to be talking about lots of calculations that you need to do involving moles. Hello and welcome to the Chemistry Made Simple podcast. I'm your host, Matthew Macario, and this is the podcast where you get chemistry confident and we take you from point A to grade A. Welcome back to the podcast. In today's episode, we're going to be talking about how we use the mole. We talked about what is a mole and why is it so important to understand a mole in a recent episode. And if you haven't listened to that yet, I would suggest pause this video and go and listen to that one first. Okay, you're back. Great, let's carry on. So we're going to talk about lots of different calculations that you can do using the mole, and you will need to do these. You'll need to do these a lot throughout your chemistry studies. They are fundamental to understanding what you can do with chemistry and to be able to do your assignments, your homeworks, your exams. There's so much in chemistry that revolves around calculations of which you need to use moles. Some of those are fairly basic, and there's some more complicated ones as well, and plenty in between. Don't be scared of the mole. Don't be scared of the calculations. You just need to practice them, get used to them, understand them, and it'll become like second nature to you. Let's start with the simplest, the one you would need to know first, and that's how to work out the relative formula mass of a compound or even of an element or an ion. The relative formula mass is the mass of 1 mole of the substance. Let's think about a compound to start with. A compound has a formula, and you need to use the correct formula, of course. That formula tells you how many atoms of each of the element are in the formula. So, for example, sulfuric acid has the formula H2SO4. And hopefully you already know what that means, but let's break it down anyway. H2SO4. The H2 means there are 2 hydrogen atoms. The S without a number after means there's 1 sulfur atom. And the O with a 4 after means there are 4 oxygen atoms. So that in one formula unit, 1 molecule of sulfuric acid, there are 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms. To get the relative formula mass, you add up the relative atomic mass of each of the atoms within that formula. Hydrogen has a mass of 1. There's 2 of them, so we need to add 2. Sulfur has a mass of 32.1. There's 1 sulfur, so we add 32.1. Oxygen has a mass of 16. There are 4 oxygens, so we need 4 times 16 and add that as well. When we add those together, we have a relative formula mass of 98.1. This is the first calculation and the most important calculation you need to do with moles is work out the relative formula mass for a substance. How about for an ion with more than 1 atom in it? Again, you do exactly the same. Don't worry that there's a charge there. That makes no difference to the relative formula mass of an ion. How about for an element? Some elements have a fixed molecule size, so don't naturally exist as single atoms or as an undefined molecule size. They have a specific molecule size. Examples include hydrogen H2. There are 2 hydrogen atoms in each molecule of hydrogen gas. When we calculate the relative formula mass, we need to include the relative atomic mass of both hydrogens. So the relative formula mass of hydrogen, H2, is 2, not 1. Other examples are chlorine, Cl2. Chlorine is also diatomic. It exists as a molecule of 2 chlorine atoms. It's a defined molecule size. When we calculate the relative formula mass, we need to include both chlorine atoms. The relative atomic mass of chlorine of a single atom is 35.5. The relative formula mass of chlorine, the element, is twice that, it's 71. For all those, we've been talking about relative atomic mass. We're talking about that in terms of 1 molecule, 1 formula unit of the substance. And if you have listened to that episode about moles, then you'll understand that the mole is that magic number that means we can just scale that up to grams for a mole of that substance. Going back to our example of sulfuric acid, we calculated that the relative formula mass is 98.1. That means that the mass of 1 mole of sulfuric acid is 98.1 grams. When we talked about chlorine, Cl2, having a relative formula mass of 71, that means that the mass of 1 mole of chlorine gas is 71 grams. How do you use that to calculate the number of moles of something from experimental data? You simply need to compare the actual mass of the substance and the relative formula mass. The number of moles of that substance is equal to the mass you actually have or used divided by the relative formula mass that you calculated, as we've just described. Going through that again, number of moles equals the actual mass you have or that you used or that you have in the data you've been given divided by the relative formula mass that you calculated. And just like other calculations, this one you'll use in different forms as well. You can use it if you know the number of moles of a substance and you calculate the relative formula mass, you can work out what is the mass of that X number of moles of that substance just by rearranging that calculation. Similarly, if you know the actual mass and you know the number of moles, you can calculate the relative formula mass if it's an unknown substance. That might be useful to help you work out what the substance actually is if you haven't been given that information. Now, it's not unusual for you to need to be able to understand and rearrange mathematical equations in chemistry. You will need to do that with a number of others, but this one is one that you'll be doing a lot of. It's not just about working out the moles if you're given the mass and the relative formula mass. You might need to use it the other way around quite a lot. What other calculations will you be asked to do? You've probably seen questions where you're given some information about a compound that has 2 or 3 elements. You may or may not be given the sample size. You'll need to be given the percentages or the grams for all the elements within the compound. And you can use that information to calculate the empirical formula because you use the percentage or the number of grams to calculate the number of moles of each element present in that compound. And from that, you can calculate the empirical formula. If you're given extra information after that, you can also turn that empirical formula into the actual chemical formula. There's also an advanced version of this where you can calculate the number of moles of water of crystallization in a hydrated salt. And in that example, you'd just be given weight loss information when that hydrated salt is dried, and that would give you the percentage or grams, and that would enable you to calculate the percentage or grams of water present in that substance, and you can work out the number of moles of water of crystallization from there. Using similar methodology to calculate the empirical formula, we can calculate percentage composition. If you know the formula of a compound, you can calculate the percentage composition of a particular element within that compound, and you do so using the relative formula mass and the relative atomic mass of that particular element, along with the number of atoms of that element within the relative formula. Another calculation we'll need to do is to be able to calculate the volume of a gas from experimental data. You do this using the ideal gas equation and using the molar volume of a gas. You need to know the temperature and pressure to be able to do this calculation. Again, you might need to calculate the volume of the gas generated, or from the volume calculate number of moles. It is another one of those calculations where you'll frequently need to be able to do it in different ways and rearrange the calculation. There are plenty of calculations you need to do related to solutions. You'll need to work out the concentration of solutions, not just in grams per decimeter cubed or grams per litre, but also in moles per decimeter cubed or moles per litre. In fact, moles per decimeter cubed is the one that we use in pretty much every other calculation where concentration is involved. And because you do a lot of experiments or deal with a lot of experimental data that involves solutions and reactions in solution, this is something that you'll use regularly, so it's important you know how to do. We use the concentration in moles per decimeter cubed in titration calculations. We also use it in all sorts of equilibrium calculations, and that includes those calculations relating to calculating the pH of weak acids, weak bases, buffer solutions, and also simply calculating the pH of strong acids and strong bases. There's other calculations we need to do related to experimental data as well, or you might consider it that they're related to the chemical equation. I talked in a recent episode about chemical equations, and if you remember, the golden rule was that you need a balanced equation. If you can't remember why, or you haven't listened yet, go and listen to that episode now. Calculations we'll need to do is to be able to calculate the number of moles used or produced using experimental data. There'll be times where we need to calculate the expected number of moles, or the expected mass, or the expected volume of a product, or calculate number of moles, mass, or volume of a reactant that we need to use. We can also calculate the percentage yield from experimental data in conjunction with the calculated maximum yield. So this means we can calculate based on how many moles we have present of reactants, what the maximum yield of a product or products are. And then we can use the experimental data of how much of those products we actually did produce to calculate the yield. Another way of using mole calculations is when we're asked to determine the limiting reagent. This is where there's a reaction that has two or maybe more reactants. So if you have the balanced equation and you have the data of the actual mass of each of the reactants, the limiting reagent is the one that will be used up first. It's limiting, meaning that once it's used up, no more of the reaction can proceed because there just isn't that reactant left, even if there is an excess of other reactants present. You'll also need to be able to do calculations related to energy changes or enthalpy changes. You'll need to know how to use the calculations in order to understand how to use standard enthalpy change data or average bond enthalpy data as well. You're going to use these in a number of ways, for example, Born-Haber cycles, or calculations related to using a Hess's law triangle. Okay, let's summarize. Today we've reinforced some of the reasons why a mole is so important. You're going to be doing a lot of calculations where you need to understand what is a mole and how do I use it in calculations. We also reinforce what I mentioned a couple of episodes ago about having to use the balanced chemical equation whenever we're doing calculations related to experimental data, a reaction that happened. Talked about perhaps the simplest calculation, but potentially the most important, is being able to calculate the relative formula mass correctly for a substance. And that might be a compound, it might be an element, it might be a complex ion. I also mentioned there are various calculations involving how to work out empirical formula or percentage composition. We also need to use the mole when using the ideal gas equation and when calculating the concentration of solutions, which we'll use a lot in titration calculations, in equilibrium calculations, in pH calculations, anything involving weak acids, buffers, weak bases. We talked about calculations from experimental data, in other words, calculations related to chemical equations. And you'll be expected to be able to do all sorts of calculations, for example, to calculate the number of moles used or produced using experimental data, or to calculate the expected number of moles, the expected mass or volume of a product, or decide the mass, moles, or volume of a reactant required. You'll be able to use experimental data to calculate the percentage yield of a product. You'll be able to use logic in conjunction with the number of moles and the mass of substances to determine the limiting reagent in an experiment. You'll also use moles a lot when doing calculations related to energy changes, and you'll come across a lot of those. Born-Haber cycles, Hess's law, for example, you'll use it for entropy and Gibbs free energy too. So that brings us to the end of this episode. And if this has been helpful, then do like and share this episode. Subscribe to the channel so you're not going to miss anything. If you want to see when I go through some of these calculations in video form, and that is the best way to deal with examples and to learn examples, then sign up and I'll let you know when I have any videos coming out that are related to doing calculations. If you want to do that, and of course you do, just go to chemistrymadesimple.net/calculations. I will put that link in the notes. When you sign up, I'll send you straight away a link for a video I did, which is a walkthrough on how to do a titration calculation. Okay, so that's the end of this episode. Let me know if you have any further questions on this topic. Feel free to comment below, and of course, do share this video with your fellow chemistry students. Look after yourselves, and I'll speak to you again very soon. Thank you for taking the time to listen to this episode. I hope it's been useful to you. And if it has, please consider supporting the podcast at our Patreon, and that's at patreon.com/chemistrymadesimple. Not only will you be supporting the podcast and seeing our updates, but there's also a community element to our Patreon, so you can connect with other students, and also you can ask questions or suggest topics for upcoming episodes too. Look forward to seeing you there, and also to speaking to you in the next episode. Until then, do look after yourself, and goodbye.